What specific problem does the Sparse Sinkhorn Token Translation (S2T2) algorithm aim to solve, particularly in the context of reasoning about molecular sequences?
The Sparse Sinkhorn Token Translation (S2T2) algorithm aims to address the issue of semantic misalignment that arises when modern large language models (LLMs), predominantly trained on English and code, are applied to molecular sequences like proteins. This misalignment occurs because the representation and frequency of substrings in molecular sequences differ significantly from their natural language counterparts, leading to poor compression quality, increased context length, and higher inference costs. S2T2 circumvents the need for parallel training data, which is often unavailable for such domains, by learning a translation between training domain tokens and new target domain tokens, using only sample data from the target domain and pre-trained LLM weights. The algorithm effectively translates target domain tokens into a sparse distribution over training domain tokens, facilitating better model performance in terms of compression and perplexity when fine-tuning on protein sequences. Thus, S2T2 provides a solution to the challenge of adapting LLMs to low-resource domains without requiring extensive parallel datasets.
How does the proposed Sparse Sinkhorn Token Translation (S2T2) algorithm work? Illustrate the methodology step by step, detailing the roles of the token embedding matrix, language model head, and the joint probability matrix P.
The Sparse Sinkhorn Token Translation (S2T2) algorithm operates in several key steps. First, it begins with a pre-trained large language model (LLM) that has a vocabulary size v, an embedding matrix E in math BBR caret versus times d, and a language model head L in math BBR caret versus times d. The algorithm then takes a new target domain dataset D and trains a new tokenizer, resulting in marginal distributions over training domain tokens mu and target domain tokens nu. Next, S2T2 constructs a joint probability matrix P that satisfies the constraints P1 equals mu and P caret T1 equals nu, which is achieved through an optimization process that utilizes a dense weight matrix C and applies a Sinkhorn-like algorithm to recover P. This joint probability matrix P is crucial as it translates target domain tokens into a sparse distribution over training domain tokens, allowing the model to leverage the pre-trained weights effectively. Finally, the new target domain LLM is defined by substituting the original embedding matrix and language model head with E equals P caret T O dot 1 mu E and L equals P O dot 1 nu caret TL, ensuring that the embeddings are on the same scale, thus facilitating improved performance in the target domain.
Can you provide a simple example that illustrates the inner workings of the S2T2 algorithm? Walk through the main algorithm steps with this example to clarify the translation process between target and training domain tokens.
To illustrate the S2T2 algorithm, consider a simple example where we have a target domain consisting of protein sequence tokens such as A, C, G, and T, and a training domain with tokens like A, B, C, etc. The first step involves training a tokenizer on the target domain, which results in a marginal distribution over the target tokens, denoted as nu. Next, we initialize a dense weight matrix C with equal values E, G, and V and apply the Sparse Sinkhorn algorithm to derive a joint probability matrix P that satisfies the constraints of matching the marginal distributions of both domains, mu and nu. Once P is obtained, we create a new target domain LLM by adjusting the embedding matrix E and language model head L, using the Hadamard product of P with the original matrices, ensuring that the scales are compatible. Finally, during the forward pass, the model predicts the next training domain token based on the target domain input, and this token is translated back into a distribution over the target domain tokens, completing the translation process. This method allows for effective initialization for continual fine-tuning on protein sequences, enhancing both compression and perplexity metrics.
What are the theoretical or practical benefits of using the S2T2 method compared to traditional approaches? Specifically address how S2T2 handles domain adaptation and what advantages it provides in terms of model transferability.
The S2T2 method offers significant theoretical and practical benefits over traditional approaches, particularly in handling domain adaptation without the need for parallel training data. Unlike conventional methods that rely on parallel datasets, S2T2 learns a translation between training domain tokens and new target domain tokens using only sample data from the target domain and pre-trained LLM weights. This approach not only improves compression and perplexity during continual fine-tuning on protein sequences, but also facilitates weak-to-strong model transferability, allowing translations learned from smaller models to be effectively applied to larger, more powerful models. In experiments, S2T2 initialization outperformed direct fine-tuning with a new tokenizer, demonstrating its superior performance in both language model quality and compression metrics. Overall, S2T2 enhances the adaptability of LLMs to new domains while maintaining efficiency and effectiveness in model transfer.
How is the Sparse Sinkhorn Token Translation (S2T2) method validated or tested in your experiments? Describe the experimental design and the metrics used to evaluate its performance against baseline methods.
The Sparse Sinkhorn Token Translation (S2T2) method is validated through experiments conducted on the UniRef 50 protein sequence dataset using the Olmo 1B English LLM. The experimental design involves training a new byte pair encoding BPE tokenizer on the UniRef 50 dataset, which reduces the length of protein sequences by an average factor of 1.82. The performance of S2T2 is evaluated against baseline methods using two key metrics: perplexity, which measures language model quality, and bits per byte, BPB, which assesses model compression. The results indicate that initializing with S2T2 yields better perplexity and BPB compared to whole model fine-tuning with the original tokenizer and outperforms both dense Sinkhorn and unconstrained token translation methods. Additionally, S2T2 demonstrates improved performance after fine-tuning, further validating its effectiveness in translating tokens for the target domain.
What results were achieved with the S2T2 method in your experiments, particularly concerning perplexity and bits per byte, BPB? How do these results compare to the baseline methods mentioned?
In our experiments using the S2T2 method on the UniRef 50 protein sequence dataset with the Olmo 1B English LLM, we observed significant improvements in both perplexity and bits per byte, BPB metrics. Specifically, S2T2 provided better language model quality, as indicated by lower perplexity and enhanced compression, reflected in improved BPB compared to the baseline methods. Notably, S2T2 outperformed the whole model fine-tuning with the original tokenizer, baseline 3, which suffered from worse BPB due to longer sequence lengths. Additionally, S2T2 initialization surpassed both dense Sinkhorn and unconstrained token translation methods in these metrics. After fine-tuning, S2T2 also yielded better perplexity and BPB than direct fine-tuning with a new tokenizer, baseline 4, demonstrating its effectiveness in model performance enhancement.